We're going to do our next section. We are going to do direction fields. So we've looked at, last time we looked at differential equations, and we didn't solve any really for the most part. What we did is we looked at how you can check that something's a solution. So imagine you've got this differential equation, very simple one. We're only going to look at first order differential equations again. And you want to visualize it. You want to have a picture of what this differential equation looks like. What does it represent? And we do that by a thing called a direction field. So it's a way to visualize this fella. So let's show you how it works. dy by dx, the derivative, can be thought of as the slope at a given point, right? The derivative is the slope of the tangent line. So you can think of it as a slope. So the slope in this case is the x coordinate plus the y coordinate. So you imagine a grid and you only take integer points because there's an infinite number and you can't do all of them. And for example, at the point 2, 1, which is here, the slope is the x coordinate plus the y coordinate. The slope is 3. So at that point there, you draw a little line whose slope is 3. Can you pretend that's the slope of 3? And then choose another point like -1, 1. And the slope in this case would be 0. So at this point here, the slope would be horizontal. That's what 0 looks like. I've got a third point, 0, 2, which is what here. And if you do 0 plus 2, you get a slope of 2. So it's kind of like that. And then at -2, 1, which is here, you get a slope of -1. And -1 would be pointing down the way. Now, can you imagine I did that for every single one of these points? Can you see why you don't want to do one of these by hand? Right, it would take you forever. But I'm going to pretend that I know what the heck I'm doing. It goes like that, then it goes like that, then it goes like that, and it goes like that. And this one is even steeper. Not quite as steep, not quite as steep. 0, then it's down the way. And this one goes like that. It's horizontal. -1, 0. -1, 1. That's horizontal. And this one goes down and down some more. This one goes like that. Then it goes like this, and it goes steeper and steeper. This goes steeper, steeper, and steeper. Not quite as steep. Positive. And that's sort of a kind of what the thing looks like. Can you visualize, the way I look at this is, couldn't that be a good way to visualize a river current? Imagine at any given point on the surface, the current is turning. So when I look at this shape, can you see there's a kind of turn going that way? Now, what you could do is you could say, okay, suppose I had a point there. It was a little paper boat, and I had a point there. What would happen to it? Well, it would go like this. Where would it have came from? Well, it came, it might have came from something like this. And you see, whatever, you could get a pathway. That's probably not a very accurate one, but a pathway for the direction field. And you are going to do a lot of questions involving in 9.2 these direction fields. So let me show you what they look like and then show you how we can make it dead easy, because we all like dead easy, right? So scroll up a bit. Here we go. Here is a direction field. That's just another way of saying dy by dx. And it's equal to this fella. And they're showing you what that direction field looks like. It's kind of nice that they're showing it, right? And we are going to sketch what these curves would look like. So when someone says y0 is 0, they're telling you that x is 0 is y 0. So they're telling me it's that point there. So imagine a little boat at that point there. Can you see the curve would go up something like this? And then it would go up something like this. Wouldn't it look like a kind of flattened U shape? Can you imagine it? Right. And you're meant to do it 4 times. And then one of these 4 pictures is the right one. So I'm going to show you a cool piece of software that does that for you. And it does it better than I could by hand. And just have to, oh, stay then. Sassing. All right, just bear with me for a few seconds. I'm trying to get into Canvas. It's being slow. Okay, I think I'm ready to show you this piece of software. Right, you should be looking at essentially our Canvas page. You see it here? Right. Direction or slope field, right?
You can't see anything.
You can't, then I need to do that again. Can you see it now? Yeah. Can you see a thing saying GeoBrow direction or slope field?
Yep. Yes.
Okay, I probably didn't click it hard enough. Right. This is the software that you're going to use for all these direction fields. Now, you put up here whatever the equation is. Oh, actually, isn't that my x plus y guy that I did a few minutes ago? Can you see all the little lines that represent the slopes at given points? You see them all here? Now, suppose they told me y of 0 equals 2. Y of 0 equals 2 would mean that you would be, come on, behave, you would be at 0, 2. And suppose the next one was y of 1, 5. Can I do 1, 5? Yeah, I can. 1, 5. And suppose the next one is at negative 2, negative 2. Right. Suppose the last one is at 2, negative 2. You see, all I do is I click on it and I move the thing. And this here would represent what that paper boat would do if you dropped it here and it followed the current, right? Either this way or that way. You see how that's much easier than trying to kind of do it yourself. And if you don't like that color, can I do red? Oh, I can make the points red. I guess that's something. Are we good? Now, there's lots of things to play about with here. I'm frightened to do too much. If I do this, it puts more dots, more little vectors in. If I choose this, it'll make them longer or shorter. And this suggests the X's and Y's. It's pretty obvious. So that piece of software is the guy that you are going to use mostly in 9.2. So it's going to make your life a lot easier. So let's pick one and try it. Which one are we doing? This is annoying. I've got the answers on and they just distract the heck out of me. Right, make that go away. Right, good. So it says sketch a direction field for the differential equation, then use it to sketch 3 solution curves. Right, so this guy says what? Y dash equals a half y. So what I'll do is I'll go to this fella and I'll change this to y dashed equals a half. Well, I guess I'll call it 0.5 y. And when I click out of this, a new direction field. And I'll just take these guys away and let's find out. Do they give us any specific points? Oh, they do. Right, so I want to go through here and here. So 0, 1, and 0, negative 1. 0, 1, and 0, negative 1. So first solution, pull it down to 0, 1. Second solution, 0, negative 1. Right, that's my answer. Now, does that look like one of these guys? And the answer is, I think it looks like that guy. Do you agree? And all that hard work was just so you could put a dot on one of 4 pictures.
Actually, wasn't it the
bottom right because it
Oh,
opened up
I
to the
didn't
right.
notice that one. What was different about this one and that
They're
one?
flipped.
Oh, it's the way they curved.
Mm-hmm.
Ah, okay. Gotcha. Let me jump into that other one just to verify what you just said. Do you see how this one curves out the way? Yeah, it curves out the way. So I should have picked that one. I wasn't paying attention. Right. Now, here is your derivative guy. And the point we're going to do is 1, 0. So what's that? Y take away 2x this time. So I'll go in here, and the derivative is going to be y take away 2x. So when I click off it, I should get the new field. There it is. Take those guys out the way and figure out what the question was again. And the question was 1, 0. Okay. So I only need one solution. I'll move it to, well, there, right, 1, 0. And let's see what our choices look like. Can you see it fits one of the pictures? And this is one of these situations where I probably need to shrink the thing rather than make it bigger. There. Can you see from these 4 pictures, the one that looks like what we had a few moments ago? The one we had looks like this, right? And if I click back into the choices, can you see the one that fits that picture, I believe, is that one. Agreed?
Yes.
Now, isn't that going to be a lot easier than doing it by hand? Okay. So here is the derivative. Here's the point. Who am I? Here is the, this one you can't do with the graphics. The reason you can't do question 9 is, do you see that there's no equation for you to use? So we're going to have to do this a little bit sneaky. Y of 0 is negative 0.5. So that means when x is 0, the y coordinate is negative 0.5. Very roughly, where my mouse is right now, would you agree that's roughly 0, negative 0.5? Now, at that point there, do you see it goes along and then it curves down? And then it goes along and it curves down. It looks to me like a hill. And it looks to me like it would be that hill. Would you agree? So it wasn't that hard. And then there's some others of the same type. Here's another example of that same problem, right? This time 0, 1. Now, if you put 0, 1 where my mouse pointer is right now, let's see what happens. At that point there, it goes along and it kind of curves up the way. And then if you go this way, it kind of goes along and it curves up that way. So it looks like a big U. And I believe it's that U. I get a feeling this homework's not going to take a long time. Might take you a little bit of time typing in the formula and that's it. Here's the derivative. Which picture is it? Now, do you see in this case, you've got 4 guys to do? A dot at 0, 1, another at 0, negative 1, another at 0, negative 3, and a final dot at 0, 3. Do you want me to do that one, or does that one look obvious? You feel comfortable about what you would do there? Or do you want to see it? You're good. Okay. I like that. Okay, here's another one. You have a formula. 4 guys. One picture, but 4 guys. You probably don't know the reference to this, but this reminds me of Mick Jagger.
The music video?
The music guy.
Yeah.
The lips.
Oh, okay. Yeah.
It just shows you how weird my brain is. Here's another direction field. Do the guy, and that's it. Do we feel comfortable about how this piece of software that I've got is going to make this section really just a matter of using the software, and for most of the time, pick the right picture, right? It's all visual. Pick the picture.
Can you briefly go over how to plot the lines one more
Sure.
time?
Yeah, I'll just pick up my own ones, right? And make one up. Okay, so let's suppose, I've got this one here, right? Let's suppose this is your differential equation, right? It says dy by dx equals y minus 2x. And let's suppose one of the points was y0 equals 2, right? y0 in brackets equals 2 means when x is 0, the y coordinate is 2. So I'll click on that, and when x is 0, y is 2. Do you see I'm moving? There we go. Do you see I'm moving my little guy to 0, 2? Let's suppose the next point was y of 1 was 3. Y of 1 was 3 would be here. Let's
I'm
suppose,
sorry. I meant plotting the directional lines on the graph. Are we going to need that in the future?
no, you use software.
All right, never mind then. Yeah, disregard.
Oh God, nobody in their right minds wanted to do what I did at the start. Remember at the start, I just kind of sort of guessed. You know, I did 12 dots and, you know, that's about 3 and that's about 2. And now this is a kind of software, probably much more advanced version, but this does the job, right? And so there's a third answer. And just for fun and giggles, let's do a one away over here. Now, if you can imagine this as a wind pattern or maybe a current pattern, if a ship comes this way, doesn't it just keep sailing north like nothing happened? If a ship sails this way, doesn't it go kind of northeasty? But if a ship does this, doesn't the current make it bend back on the way you came? So you can imagine wind patterns and currents and magnetic fields all having this kind of shape to them, and why differential equations are really good at modeling things that look like this. If this is good, I'm going to call this section finished. Is there in and about it? 9-2 differential direction fields.
This is probably the easiest section we've ever had, to be honest.
Nothing wrong with that. I wouldn't argue with it. I like it. If you felt that, I'm happy. Okay, just moving some windows around and closing some other windows. So you can bear with me for a few moments. What we need to do now is actually solve our first differential equation. Well, second, we did a kind of baby one earlier. So give me a few moments to get my act together. And we are going to solve a differential equation using a technique called variable separable. So here we go. This is going to be section 9.3. So we're going to look at variable separable differential equation. So here's a definition of what that looks like. A first order differential equation that can be written as dy by dx equals f of x over g of y is called variable separable differential equation. So if you can get a differential equation and you can algebraically turn it into a guy that looks like that. Now, do you notice that it's just dy by dx equals a single fraction, and everything on the top has to have x's, and everything on the bottom has to be y's? If you can get that to happen, you are looking at a variable separable differential equation, and we'll show you how you solve those. So let's give you some examples of what they would look like. Would you agree that fits into the shape? X is on the top, Y is on the bottom. Here's another one. Variables separable. Are you comfortable with what a variable separable looks like? So if someone just said solve this differential equation, but you noticed it was this guy. So you might say, well, how do you solve them? Let's pick an example. Suppose I wanted to solve this differential equation. Now we are about to do some really sneaky algebra. And it is going to look like cross multiplication. Technically, it's not, but it will look like. Do you see what I have done there is turn this into integrals? And what I was getting at, do you see these two guys here? And you see these two guys here? Doesn't that look kind of like cross multiplication? And then you stick an integral on them. Now, when you solve this differential equation, don't expect, unless you're really lucky, to write down the answer y equals x cubed plus 1. You don't tend to get that lucky. What you tend to get as your answer is what's called an implicit equation. X squared y plus y cubed equals something, right? Or y cubed plus y equals something, right? And that's okay to get that, because that's what your solution is. Anything that has a mixture, you know, if somebody has said that's, put a 1 in there, that's, yeah, make it messier. That's an example of what I'm getting at. That's okay. That is the solution. I mean, that's a curve. If you put it in any software, you can draw it. So let's see. Integrate. Power rule. Integrate. And you need a c, but you only need 1 plus c. And always give it to the x's, right? Always give it to the right-hand side. Now, you might say, well, what about the plus c that would be here? Well, if it was here, couldn't I just bring it over here and make a new c? So you only need 1 arbitrary constant. Now, in some situations, as ugly as that may seem to you, that is the correct answer. The solution to this differential equation is this implicit. You might see it written, and to me, I don't see a lot of benefit, but you might see it written like that. These are all equivalent. You might see it written like that. And this might look like a contradiction, but it's not. That, in fact, is much more likely than this. How can that turn into a plus? Now, don't think normal algebra, because normal algebra, shouldn't you, if you subtract it, shouldn't that be what you get? But this isn't normal algebra. We're thinking of C as being an unknown number, right? If I bring it over here, isn't it take away an unknown number? Well, isn't taking away an unknown number the same as adding a different unknown number? So that's how it works. The algebra of the plus C's gets weirder later on. But sometimes you can get a variable separable where you can actually rewrite it as y equals. And if you can, you should. So let's do this fella. Right, variable separable. Do the crossover. Isn't it a bit like U subs, where you do the crossover and then stick an integral in front of it? It's a bit like that. Now, power rule. Are we good so far? Now, I'm going to do some weird algebra with that C. Eventually, I'm going to get y on its own. Shouldn't I multiply both sides by 3? That would get me closer to it. So -3 cosine x plus 3 upon 2 x squared plus c. If you don't know what something is, don't you still not know what 3 times something is? And doesn't it just make it prettier that it's just a plus c and not a plus c squared, over 42 or something, right? You can imagine doing all sorts of calculations to it. It's just a sum you don't know, so you might as well just keep calling it plus c.
Yeah, you wouldn't have like infinity squared.
Right, you wouldn't want that. Now, how do I get y? What do I need to do to both sides to solve for y?
Cube root.
Yeah. So can you see that in some questions, and I'm quite happy with that. As long as WebAssign's happy with that, I'm happy with that. If WebAssign's not, then you're going to have to figure one of these guys out. But that's totally okay, right? You can't fix that, right? There's no easy algebraic way, would you agree, of turning that into a y equals. So you don't try. But in other questions, can you see that there is a way to do it? And you should at least attempt. At least give it a shot if you think it's doable. And this here would be the solution to that differential equation. Now, actually, isn't it the general solution to this differential equation?
Somebody had a question in chat.
Oh, can you read it out to me? I've got too many windows here. It's hard for me to do it.
Yeah, they're saying, would you multiply C by 3?
Well, you technically are multiplying it by 3 and then just saying 3c is something I don't know, so I'll just call it plus c again. And the purists amongst us, and call that C1 and then call that C2 and then call that C3. But I don't think most people do that. So I just call it plus C. And it's good to go. Now, suppose I told you, because we might, that y of 0 is 5. This is the guy that's sometimes called the boundary or initial condition. Right? So isn't that guy's job to tell you who C is? Right? This extra piece of information. If you did this in the direction field software, and then you put in 0,5 as your dot, wouldn't there be a curve drawn? And that curve is unique. And that curve is unique because this C and only one value of C will match this curve. So let's see how that would work. I guess I'll write it down again. We start with our original general solution. And we use the fact that this boundary condition says that when x is 0, y is 5. So this guy is 5. Right, cosine of 0 is 1, so you get -3. Nothing squared is nothing, so you get nothing plus c. If you cube both sides, and then add 3 to both sides. Do you see that we now know the value of C? We solve for C. So you put y as 5, you put x as 0, and then you solve for C. In this case, cubing both sides gets rid of the cube root. Adding 3 to both sides gets this. And that means we now have the cube root of -3 cosine x plus 3 upon 2x squared plus 128. And when that happens, we call this the particular solution to that differential equation. Are we cool so far? Okay. Of course, you know it's not going to stay too simple too soon, right? They're going to muck about with this, and so let's muck about with you right now. This is like question 1. Here is our derivative, and uh-oh, it ain't a fraction. Right, it's got to be everybody on top has to be an x, right? Everybody below has to be a y, and this doesn't look right because it isn't.
Can we put it over y to the -2?
You nailed it.
Oh, nice.
That's exactly what you did. So can you imagine that in some questions, aren't you going to have to do a little preparatory algebra? The guy they give you isn't a fraction. I have to make it a fraction. So are you comfortable, everybody, about the y squared becomes a y to -2 on the bottom? Right. Now, the guy I call the crossover happens. Okay, that's pretty straightforward. Be a bit careful here. Remember integration power rule. If you add 1 to the power and divide by the new power, you get that. And this, you add 1 to the power and divide by the new power, and the right-hand side gets a C. Are we comfortable with that? Okay, now, this guy has a bit of work to be done. This guy can be written as y equals. I'm 100% sure. If there's only one y here, would you agree it must be able to be somehow or other algebraically rewritten as a y equals? So I am going to rewrite this guy like that. Okay, y to -1 is that. I'm going to take care of a little bit at a time. I'm going to multiply both sides by -1. Uh-oh, do you see the plus C thing happening? You know the funny algebra of C? Yeah. How will I get y?
Move everything on the right to the denominator.
Okay, that's a good way of saying it. Some of you might be thinking that, but isn't that him anyway, right? So it's the same thing. Here's your answer. We cool with that question now? Let's move up the fig chain, make it a little bit harder each time. And by the way, the questions in the homework sometimes call the guy dy by dx, sometimes call him y dashed. And this is what the question looks like that I'm saying. But this is what I write. Can you see that you really need this notation so you can do the crossover and all that stuff, right? This notation hides that. Now, the first thing I'm doing, I think, is pretty straightforward. would you agree the first thing you have to do is get dy by dx on its own, right? Now, this is not a fraction, but we've seen that problem before. And it needs to be a fraction, agreed? And the x's are on the top. So how do you fix the e to the y guy?
Move it to the denominator and change it to e to the -1.
Agreed? You know, like the y squared became a y to the -2 on the denominator. Right, now we've got the variable separable. I'll do the crossover. Integration hat is on. If you integrate e to the -y, you do get e to the -y, but you also get something else as well.
Negative in front.
Agreed. And this guy, you add 1 to the power, divide by the new power, and there's our plus c. Is this question capable of becoming a y equals, even if you're not sure how to do it? Is this question capable of being turned into that? Great. Isn't the clue there's only one y? That's how I think about it, right? If there's only one y, I should be able to do it. Any suggestions for what my first step's going to be? What should I do next?
Can't you take like the natural log or something?
Oh, that's coming next, but before that, you're right.
Multiply it by -1.
Yeah. And won't I call that plus c? And if WebAssign decides to call it -c, it's because WebAssign's stupid. It's software. It's not human. This is the way you typically do it. Now, someone said, I think it was Sean, that the natural logs kick in. Now, if you take the natural log of both sides, that's what you get on this side. What do you get if you take the natural log on this side?
-y.
Yeah. Which is good, isn't it? Because it's getting us closer to being y on its own. Can I just do the multiply everybody by -1 thing again? That is a totally acceptable answer as far as I'm concerned. If WebAssign is being really awkward, and I hope it's not, but you can never be sure with WebAssign, they might write it as that. Do you know a negative log is the same as a log of its reciprocal, because it's basically that guy to the power of -1. So we're really just tweaking what the answer looks like. I think the top one is totally fine in my book. Hold on just for a second. I'll put on the solutions here. And that gives me an idea what I've lost the damn thing. Oh, good news and bad news. The good news is that WebAssign is quite happy with this. Do you know what the bad news is? WebAssign is calling it -c. They don't do the special C algebra. Now that is going to be a pain in the butt, because that could mean, can you imagine there's going to be some questions where C ends up being something weird like that? Because you have to double both sides and divide both sides by 3 and multiply both sides by -1 and who knows what else. That is annoying, but it is what it is. I'm just scanning through to see if they do that often. Oh, the good news is after question 5, you're going to do particular solutions. So when you do particular solutions, C turns into a number, so it doesn't really matter how you write it, it's going to work. So be careful for questions 1 to 5. And after that, it won't matter. Because whatever way you write it, that's just going to end up being plus 20. And it doesn't matter if you write it my way or their way, it's still going to eventually be plus 20 when you do a particular solution. Are we good for today?